Now let's do a little bit tougher one. So I'm going to scroll down here and we're going to look at number 82. This question says, determine the volume of carbon dioxide gas at minus 18 degrees Celsius and 95 kPa produced if 30.0 grams of butane burns in excess oxygen gas. This is a combined stoichiometry question. It has a gravimetric part involving mass, and then it also has a gas component. Okay, and I see here I don't see STP or SATP. I'm given a specific set of conditions, and this is going to tell me I'm going to need the ideal gas law to solve this. Okay, so let's start out where we always need to start out, which is a balanced chemical reaction. So you guys go ahead and do this. This is a combustion reaction. Pause the video now. Build your balanced chemical equation. Okay, combustion. Butane gas C4H10 burns in excess oxygen to produce, oh, it doesn't tell me, but you guys should know that I'm going to get the most common oxide of each of those elements in the fuel, okay, in the butane. So the most common oxide of carbon is carbon dioxide. So I'm going to get some CO2, and the most common oxide of hydrogen is water. So I'm going to get some water vapor as well. Okay. And so now to balance this out, I kind of like to start with the highest numbers and work my way backwards. Another thing that sometimes I like to do for these reactions is CHO, C-H-O, carbon, hydrogen, always oxygen last. So let's use that method. So I got 4 carbons on my reactant side. I'm going to need 4 on my product side. Carbons are good. Hydrogens, I got 10 on my reactants. I need 10 on my product side. So I'm going to throw a 5 in here. And so did I say 4? I meant, did I say 10? Anyways, 10 hydrogens on each side. And now I'm going to do my oxygens last. And so for this one works out well because if I get an even number on my product side here, I'm money. If I get an odd number, if I want whole number coefficients, I gotta double everything. In this case, I don't have to because I have 5 oxygens here, okay, and I have 8 oxygens here. Oh, so I do have an odd number here. Okay, I do have an odd number. So I'm gonna end up with 13 oxygens. So I can do 13 over 2 for my oxygen on my reactant side, or I can just double everything if I want whole number coefficients. So I'm going to say, okay, 2, 13, this becomes an 8, and this becomes a 10. Okay, now some teachers don't mind if you use fractions or decimals in your coefficients. I prefer whole numbers, and that's what you end up with there. Okay, so now let's write down our given and our required information. So right now this should be jumping out at you guys. I have a minus 18 degrees Celsius. You guys need to convert that always to Kelvin. Okay, so to do that, I'm going to add 273. Some teachers might ask you to do 273.15. Some teachers might just stick with 273. Let's just do 273 for us. So if I do minus 18 plus 273, I get 255 Kelvin. kPa is good for me. And okay, so let's write down, we have 30 grams of butane. We have, we're looking at carbon dioxide here. So we have 255 Kelvin. We have 95.0 kPa. And I guess that's all. That's all that we have. Okay. So I want to find the volume of carbon dioxide gas. Okay, that's what I'm looking for. And so I'm going to start with my given. Okay, my given is here. And so I'm going to start with this 30 grams. I'm going to change my color. I just don't like writing in red for some reason. Okay, so I'm going to start with my 30.0 grams of butane, C4H10. And my first step always in stoichiometry is find the number of moles of your given. And so I'm going to do that by converting 2 moles from grams. And so that conversion factor is a molar mass. So I need the molar mass here of butane. If I want to go from grams to moles, I need the molar mass. And so the molar mass of butane is, I already calculated it, it's 58.14 grams per mole. Okay, I'm going to put my C4H10 in here. Okay, so now I've converted to moles of butane. Okay, and now the stoichiometry comes in. I'm going to jump using my molar ratio from butane to carbon dioxide. So what I want goes on top. I want CO2, and I have C4H10. Okay, and now I have moles of CO2. Now, for for most of us, I would probably calculate the number of moles here and then insert that into my ideal gas law. You could also use this, do it using unit analysis, and maybe I'll show you that at the end. But let's get our number of moles here, and then we're going to put that into our ideal gas law. So let's do that. So I'm going to take my, turn on my calculator here. 30 grams, okay, times 1 over 58.14 times 8 over 2. And I'm going to get this number, 2.064 moles of CO2. Okay. Now I'm going to take that number. I'm going to throw it into my ideal gas law. So if we remember ideal gas law, PV equals nRT, and I am solving for volume. So I need to manipulate the formula to solve for volume. Volume is going to equal nRT over P. And so let's plug in our numbers and see how we do here. So N is my 2.064 moles of CO2, and R is in your data booklet. It's your ideal gas constant, 8.314 kPa liters per mole Kelvin. And then I also need my temperature, 255 Kelvin. And then at the bottom is my pressure, 95.0 kPa. So let's make sure we did this right and see if all of our units cancel out. Moles are gone. kPa is gone. Kelvin is gone. And liters are left behind. Perfect. So when I plug this into my calculator, let's use that. I'm going to use that raw value that I got for my moles, that 2.0639 blah blah blah, and multiply that by 8.314. I'm going to multiply that by 255, and then I'm going to take that number and I'm going to divide it by 95 kilopascals, and I'm going to get the answer 46.06. So the answer here is 46.0. We really rounded to 46.1. And I think that is probably because we used 273 for Kelvin instead of 273.15. But there you have it. Okay. Now, there is another way to do this just using unit analysis, and I can show you guys that right here. So let me just go back up to this. Let me change my pen here. Hello. Ooh, this video is getting long. Holy. Those of you guys who are still here, I love you guys. You guys are awesome. So we can do the ideal gas law in here. And so what I need to do in order to do that is I'm going to take my 8.314 kPa liters per mole Kelvin. And the reason I put that on top is because liters is on top here, and I want liters. Moles is on the bottom. Now I can get rid of moles. Okay, so now I'm just going to get rid of all my other units that are in there. So kPa, it's going to go on the bottom, 95.0 kPa, and then so that's gone. And then I just need to get rid of my Kelvin. So I have my 255 Kelvin here. That's going to be gone. And I'm going to be left with liters behind here. And when I do that calculation, it's all the same math. And I'm going to get the same answer as I got right here. So a couple problems, long video. But hopefully that helps you guys out. And good luck. See you next time.